We continue with section 1.9. This is the last video for this section. There are 3 examples. So example 3, let the transformation be defined by this relation. And so what the question is asking us is find a vector x such that t of x equals -1, 4, 9. So t of x is equal to this vector. In other words, the vector x is mapped onto the vector -4, 9. Okay, so how do we do it? Well, first thing, try to understand how to figure out the transformation is between which 2 sets. So here you notice that t of x, and we see only 2 components. So this means this is from R2, and when we come on the right hand side, the vector given here, it has 3 components. So so it means this is from R3. In other words, the transformation t is from R2 to R3. So how do we solve this problem? Remember, the first thing we should look for is the standard matrix for the transformation. How do we do that? We find the images of the standard vectors or the unit vectors on the axes. So there are only 2 axes because we are in R2. So there will be 2 vectors, 2 such vectors. One is 1, 0 and other is 0, 1. So when we try to find the image of 1, 0, which is denoted by E1, we end up getting 1, -1, 3. How did I get this? Well, basically I just plugged it in here like I showed you in the previous example. So for the first one, which is E1, which is 1, 0. So if you go here, x1 is 1, x2 is 0. So I get 1 minus 2 into 0 at 1. Then -x1 plus 3x2, so I get -1. And then 3x1 minus 2x2, so I get just the 3. So my first column will be, my matrix A will be 1, -1, 3. In the same way, I find the image of E2, which comes out to be -2, 3, -2. So what this question is saying is find x such that t of x is equal to that. So remember, t of x, we have defined it by a times x. So in other words, we are saying we need to find x such that ax is equal to -1, 4, 9. So this is what we are looking for. And then but what does that mean? It means we need to solve a system of equations. Ax is equal to b type thing. So what do? We take the coefficient matrix A, and then we augment the B matrix with that, or the B column vector with that, and then we can do our row operations. So this is what I did. This is A. This is the other vector B, let's call it. So I augmented, and then doing the row operation, I've got to the row echelon form, and then I did the back substitution, and I got a unique vector x as a solution. So we might end up getting no solution, or we might get one solution, or we might get infinitely many solutions. Okay. The next example is saying determine the transformation t given by this relation, and determine if this is 1 to 1 and on to, and justify your answers. So in order for it to be 1 to 1, if you recall, there are several way or many paths along which we can go and figure out the solution. But since we are dealing with transformations, the matrix A is important, the standard matrix of the transformation. So first thing we do is we try to find A. So again, we have done some examples. I hope you guys now understand how to find A. So we will first figure out what the transformation is between what sets. So here I have a 3 component vector. So this is means T is from R3 to, okay, on this side I have 2 component vectors. So I have, this is from R3 to R2. Okay, so it means we will have 3 base vectors which we can convert to like a 2 component vector. So TE1 gives me 1, 0, TE2 gives me -5, 1, and then TE3 gives me 4, -6. I put them in as columns of matrix, and this is my matrix A, and now I'm trying to find solution of AX is equal to 0. So from theorem 11, if T of x is equal to 0 has only the trivial solution, then the transformation is 1 to 1. Okay. So we try to solve it, and we end up getting that this is there is a free variable here. The x3 is free, so which means we will not get just the trivial solution, we will get more than that. So in other words, this system has at least one non-trivial solution. Hence, by theorem 1, we can say that T is not, theorem 11, we said T is not 1 to 1. Okay, then it also asks you, is it onto? So for onto, if we can show that, if we can show that columns of A span R2, then this transformation will be onto. But there are 3 columns, and the number of entries in the columns is just 2. So the size of the column and the number of columns is different. So this is not linearly independent. So they do not span R2. Hence, this is not onto. Okay, the next and I think the last example. So it says the standard matrix of a linear transformation is given. Determine if T is 1 to 1, and then the question is, does T map R4 onto R4? Well, because A is a 4 by 4 matrix, so now we know that T is from R4 to R4. Okay, so we start with the matrix and we try to get it in the echelon form. Now, if you want, you can augment the 0 vector here, because we could be showing that we could be trying to find the solutions of AX is equal to 0. So now, once I got here to the last matrix after which is in the row echelon form, I noticed that each row has a pivot. So since each row of A has a pivot, this means the equation AX is equal to 0 has a unique solution, and that solution is only the trivial solution. Okay, so which means that the transform T is 1 to 1 by theorem 12. What about onto? Now, since every row of A has a pivot, the columns of A span R4 by theorem 4 of section 1.4, and then Therefore, T is onto, and T spans are 4.